Hello everyone, my name is Anneke Dittmer, and in the next 15 to 20 minutes we are going to explore together how you can incorporate environmental effects in your ORCA calculations. Before you create a model of your chemical system, you typically ask yourself, how can I calculate this in the most accurate way? And as an avid ORCA user, you probably come to the conclusion, let's use something like couple cluster or maybe any other type of chemically accurate method. However, sometimes the most accurate method doesn't really help you if you do not model the environment in which your system is in accurately. And this environment is rarely vacuum. It is way more likely that it will be a solvent or maybe even an extended system like a solid. These are the two types of environment we want to explore today, or more accurately, solvents and ionic crystals. But what do solvents and ionic crystals have even in common? You probably will answer this with that they both have long-range effects of electrostatic nature, but that is not the answer that I'm looking for. I think that for both systems, we have a clear idea how we can model this environment. For solvents, we typically go for an implicit solvation model, or maybe for an explicit solvation model in rare cases using molecular dynamics, for example. And for ionic crystals, we typically go for periodic models. What I want to do today is to challenge these standards a little bit by introducing you to a mixed implicit-explicit solvation model in ORCA, as well as an electrostatic embedding model, namely the ionic crystal QMM, to model ionic crystals. Let's start with solvation. As I already mentioned, the most common way to include a solvent in your model is by using it as an implicit solvent. So you only incorporate its dielectric constant in your quantum chemical model. This is a really efficient way, and there are also a lot of advances in this area in ORCA 6. Miguel is going to talk about that tomorrow. I would also recommend listening to his talk. However, a huge shortcoming of implicit solvent models is that we are completely missing the local interaction between solvents and solutes. This is something that would be covered by an explicit solvent model. However, these are typically really expensive, and already incorporating the first solvation cell, not even talking about the bulk of the solvent, will probably diminish our accuracy because we can't go to really high accurate quantum chemical methods anymore. So what we are striving here for is the best of both worlds. A mixed model of implicit and explicit solvations, only having the minimum number of necessary explicit solvent molecules. With that, we can still go to higher accurate quantum chemical methods, but are not missing some important solvent effects. However, before I'm going to show you how you can create such a model, we first have to answer the question, how can we include explicit solvent molecules in ORCA 6? This is something that was not available in ORCA so far. I will briefly show you how to do this for the example of histidine with 25 explicit water molecules. First, you have to specify the implicit solvent in your ORCA 6 input file, so in our case, water. Then, in the solvator block, which is the name of the explicit solvation tool in ORCA, you have to specify the number of explicit solvent molecules you want to add, so here 25. If you just run this calculation, ORCA will generate a histidine model with 25 explicit water molecules, simple as that. You can not only do that for water, but really for any other type of solvent available in the ORCA library. And further, you can also add explicit solvent molecules that are not in the library by just simply adding the path to the structure file of the solvent. In these cases, as a propanol, we would recommend using then an implicit solvent with a similar dielectric constant. Now that you know how to run such an ORCA calculation, you're probably wondering, how does ORCA even know where to place the explicit solvent molecules? So ORCA has two different ways of doing that. The first one is the semi-stochastic mode. Here ORCA places the explicit solvent molecules somewhat randomly in a sphere around the solute. On the fly, the EEQ charges of the system are calculated, and based on that, the electrostatic interaction between the solvent and the solute. This is done so that the solvent can be placed in an optimal distance to the solute so that the electrostatic interaction is overall maximized. Therefore, this approach is semi-stochastic and fully stochastic. However, the on-the-fly calculation is essentially at zero cost, so that the histidine plus 25 explicit solvent calculation on the XTB level can be performed in less than 1 second. This cheap approach allows you to add a significant number of solvent molecules, as here shown for histidine with different solvents, to your calculation, or even add a bunch of water molecules to biological relevant systems. While this approach is not only useful, but also surprisingly accurate, there is also a more accurate approach of the solvator in ORCA using the Docker. You probably already had a chance to see Bernardo's talk before mine, where he introduced the Docker in ORCA 6. He also did an amazing job implementing the entire solvator. Since I already introduced the Docker, I will only say here that the solvent molecules are placed by using swarm intelligence. Local minima are found by docking the solvents in different positions around the solute, and then the lowest local minimum is determined. This approach is obviously not as cheap as our semi-stochastic mode, and the calculation time increases with each explicit solvent molecule added. So for our example of histidine plus 25 water molecules, the total calculation time on the XTB level is 56 minutes in total. However, this approach brings us closer to our overall goal of finding an optimal mixed explicit-implicit solvent model with only the minimum number of explicit solvent molecules necessary. Here the question remains, how do we identify this minimum number of explicit solvent molecules? For that, let's have another look at the histidine example with the 25 water molecules docked to it. Which of the water molecules do you think are only necessary? I would say only those which are interacting most strongly with the molecules, so probably those really close to the functional groups of the histidine. But how can we quantify that? One way is to calculate the pair interaction energy of the solvents with the solute. However, we docked the molecules on the XTB level. As you probably know, this is not a good level to calculate the pair interaction energy accurately. So what we are going to do is to calculate it on a DFT level. But we're going to do a simplification here. Instead of calculating the solvent-solute interaction with all the other solvent molecules, we only calculate the pair interaction between the isolated solute and solvent pair. Seems like a huge simplification, sure, but trust the process, this will work. So we then calculated the pair interaction energy between the water molecules and the histidine on the R2scan3z level. We defined all water molecules with an interaction energy of minus 1.5 kilocalorie per mole or lower as strongly bound. With that, we end up with 4 water molecules that interact mostly with the polar sides of the histidine molecule as expected. After then optimizing the structure on the DFT level and treating the rest of the solvation effects with implicit solvation, we end up with this really efficient explicit-implicit solvation model. Here are all steps that we did to find all of the strongly interacting water molecules summarized. That to be said, you can just iteratively repeat step 2 and 3 until you're sure that you found all necessary water molecules. So you don't have to add like 20 or 50 water molecules in step 2, you can start with 5, figure out if you found strongly interacting water molecules and repeat the process until you're sure that your system is converged. But how good is this protocol? And particularly also, how good is the ORCA 6 solvator in general? We can check that by benchmarking against already existing protocols. For example, this one developed by Maren Podewitz and co-workers. They identified solvation sites using free energy-based identification with the molecular dynamic model. For this urea example, they identified the relevant solvation sites and by that also identified 6 relevant water molecules. Comparing that to the ORCA 6 solvator and our protocol to identify strongly interacting water molecules, we can see that we are placing the 5 relevant found water molecules as the same position as the 5 most relevant ones found using molecular dynamics. So these 2 results match really well. But this is not an exception. We also tried this with all other examples in the paper and got either comparable or identical results to the study with molecular dynamics, as in this example. But what about reality? Do we also get results that match experiment? As you can see for the example of helicin, where the experiment identified 1 interacting molecule at a distance of 2.5 Armstrong, you can find also 1 interacting water molecule in our simulation at a similar distance. If you're still not convinced, here's a fine example, where we compared to a crystal structure including water molecules, and again, we get a strikingly similar result. With that, I would like to conclude this first part of my talk. I hope I showed you how you can use the new solvator in ORCA 6 and how you can use it to make an efficient model combining implicit and explicit solvation. I believe that for most of you, it's quite reasonable why we use the combination of implicit and explicit solvation to model environmental effects of a solvent quite accurately. However, I'm pretty sure that a lot of you already questioned from the beginning of my talk why we should use something like an electrostatic embedding approach to model ionic crystals instead of really well-established periodic calculations. The answer to that is that we do not want to model the environment more accurately like we wanted to do it with the solvent, but make more accurate method applicable to the crystal environment. We have this wide variety of highly accurate molecular methods in ORCA available, which are often not directly applicable to solid-state systems. This is not only the case because they are not available in periodic codes, but often also because the theory is not as easily transferred to such approaches. So to make them applicable to ionic crystals, we have to use an electrostatic embedding approach. Therefore, our goal in the second part of my talk is to find an approach that allows us to apply the molecular methods available in ORCA accurately to crystals. How can we model ionic crystals with ORCA 6? So as I already said, the answer is in using an electrostatic embedding approach, but not any electrostatic embedding approach, but the ionic crystal QMM approach as is implemented in ORCA. Here we have to create a quantum cluster as the center of our model. This has to be representative for the bulk property of the solid-state system we want to calculate, since this is the part where the actual quantum chemical calculation takes place. The long-range effects of the crystal are then imitated by a large field of point charges. These point charges do not only have to represent the electrostatic long-range effects by creating a homogeneous charge distribution imitating the ionic charges of the quantum cluster, but also having to make sure that our overall system is neutral, because a large solid is typically neutral in charge. Between the point charge fields in the quantum cluster, we are introducing a boundary region of electronic core potentials. They should prevent charge flow between the quantum cluster and the point charge field, as well as minimize surface effects of the quantum cluster, so that overall our electrostatic embedding approach gets the closest to an ideal ionic crystal. The first step in building such a model is to create a large supercell from which we will then cut subsequently the quantum cluster boundary region and the PC field. We can do this by taking a ZIP file of our crystal, here we will use sodium chloride as an example, and creating a supercell from it using a program such as Crystal or Vesta. Then we can manually cut out the different parts of our model. This is one way to do it. Another one is just to use the ORCA subprogram Crystal Prep. To create the supercell and then subsequently the entire electrostatic embedding model using Crystal Prep, you must first create a generic Crystal Prep input file. You can do this by simply specifying the name of the desired input file. So we will name it here NaCl imp, since we want to create a sodium chloride model. And then you can generate this input file simply by using the keyword gen input as is shown on the slide. The then generated input file will look something like this. You can fill it in according to the model you want to create. In the part of the shown input here, we first specify that we want to generate the supercell for our example using a ZIP file with a given name. Again, here NaCl. Then define the size of the supercell. Running this input file as it's shown here with Crystal Prep would generate us a supercell of the given size. However, we also want to directly create the input file for our ORCA ionic crystal QMM calculation with Crystal Prep. So we also want to predefine the different regions of our model. We can do this by filling in the rest of the generated input file, specifying the cluster and boundary region size, as well as the charges and that we want to generate an ORCA ionic crystal QMM input file. By running this input file with Crystal Prep, as shown at the bottom of the slide, we then generate all the necessary structure and input files. This generated input file would also include the force field file you need for any QMM calculation in ORCA, including the ionic crystal approach. Since you might want to create the model by hand instead of using ORCA Crystal Prep, I will briefly show you how to create this force field file using ORCA MM. It is quite simple. You just define that you want to run ORCA MM, then that you want to create a force field file using makeFF, then define the structure file of your crystal, and then the charges of the different ions. This will then create the force field file with the predefined charges. If this has not already been done automatically by Crystal Prep, the next step is to generate your ORCA input file. In this input file, you first have to define that you want to run an ionic crystal calculation, together with the method you want to apply to your system. Then in the QMM block, you have to define the name and path to your force field file. Down in the XYZ file line, you have to specify the name of the structure file of your entire supercell. Here be careful, because the charge and multiplicity defined in this line are not the charge and multiplicity of your entire supercell, but only of your quantum cluster. The quantum cluster you also define in the QMM block. Here we just want to create a cube of 8 NaCl ions. Besides the quantum cluster, in the QMM block we also have to define the size of the boundary region by specifying the number of ECP layers, and also specify that we want to optimize our point charges as well as that we want to have an overall neutralized system, as we defined as a necessity already in the beginning when introducing the model. Now that we know how to create an Ionic crystal QMM model to make the molecular methods applicable to solids, we first need to check whether these models are a reasonable approach to the solids, which we can do by comparing them with periodic calculation, for which we already know that they define solid-state systems quite well. We want to compare our model based on a single-point calculation to a periodic calculation. However, whatever property we are going to compare in the end, we can just not run one input file of our Ionic crystal QMM approach. The reason for that is that we have to make sure that whatever property we are comparing is converged for the quantum cluster size we are using. So what we need to do is to run multiple calculations on different quantum cluster sizes until we can make sure that the property we are calculating is converged with respect to the size. We have done this conversion here by calculating the optical band gap of lithium chloride using time-dependent DFT. And you can see that the band gap is not only converging with the quantum cluster size, but also approaches the result predicted by the periodic calculation using the same functional. This is not only the case for lithium chloride, but also, for example, for zinc sulfide. So from these results, we know now that we can get, with our electrostatic embedding approach, comparable results to the standard of periodic calculations. However, our goal was not to be as accurate as periodic calculations, but to be able to use more accurate methods that are typically only available to molecules. So instead of using DFT, we are going to use now an equation of motion coupled cluster method and recalculating the band gaps. For the examples that we already discussed, we get then quite well agreement with the experiment. We did that for a bunch of different kind of solids. And you can see that overall, for the equation of motion coupled cluster method, we get an error of approximately 0.2 electron volts. This is also what we would expect for the same method for molecules. Therefore, we reached our goal to find an electrostatic embedding model with which we can accurately apply the methods available in ORCA 6 to ionic crystals. Before I conclude my talk here, just a quick comment. As you may have noticed, the study I just talked about was conducted in 2019, so in the development phase of ORCA 5. But why am I talking about it today at the ORCA 6 release event? The reason is that we have since then conducted a number of studies using this Ionic crystal QMM approach successfully. Also, we have improved on its efficiency in ORCA 6. Pauline will talk about that tomorrow. I would also recommend listening to her talk. With that, I would like to conclude my presentation. I hope you learned how to model explicit solvents and ionic crystals in ORCA. If you're interested in learning more about either of these, please check out our tutorials. I would like to thank all the people who put a lot of effort into developing and testing these methods, and I want to thank you for your attention.